For each positive integer n, let f1 of n be twice the number of positive integer values, divisors of n. So for example, f1 of 6 would be 2 times the number of positive integer divisors of n. 6 has 4 divisors, 1, 2, 3, and 6. So it's 2 times 4, or 8. And for j greater than or equal to, greater than or equal to 2, then fj of n is f1 of fj minus 1 of n. In other words, we can rewrite this as fj of n is just f of n j times, or like f of f of f, right? Of f of n, something like this, where there are jf's. Anyway, that's basically what this recursion is telling us. Just apply f1 one more time as you increase j by 1. So now that we have this, we want to find how many values of n less than or equal to 50 is f50 of n equal to 12. What I would do here is kind of just try some small values, see where it goes. Because we do expect there to be a lot of cycles here because divisors are usually way less than the actual number itself. Anyway, we have, for example, 1. Where does 1 go? Well, 1 has 1 divisor, so it goes to 2. 2, as well as basically every prime, right, between 1 and 50, right? So up to 47. These all have 2 factors, so they go to 4, okay? 4 has 3 factors, which makes it go to 6, and we already said f(1)(6) is 8. And 8 has 4 factors, so 8 actually goes to itself. Okay, the next number not on this list is 9, the first composite number that is not listed here. 9 has 3 factors, so it actually goes to 6. Okay, so you see a lot of numbers go to 6 and then 8 and then looping at 8, which means that we're probably not going to get a lot of numbers where it's 12. Anyway, 10 has 4 factors, so 8. 11 is prime. 12 goes to itself, right? Because it has 6 factors. It factors as 2 squared times 3. So the number of factors 2 plus 1 times 3, 1 plus 1, which is 6. So 6 times 2 is 12. So 12 goes to itself. And what does it mean for something to eventually get to 12 after a bunch of applications of f? Well, then it has to reach some number with 6 factors, okay? So to get here, we need some number, right, with 6 factors. And how can we do that? Well, let's just, right? And to get to some number with 6 factors, we can consider like what numbers this could be. So essentially what I'm saying is we can work backwards from 12 and say that we have to, before 12, you have to be at some number with 6 factors, which could be 12. So let's take a look at all numbers with 6 factors, okay? Numbers with 6 factors are either of the form p to the 5 or p times q squared, where p and q are distinct primes, right? Because p to the 5 has 5 plus 1, p times q squared is 1 plus 1 times 2 plus 1. So that's 6, and that's 6, okay? So for p to the 5th, the only case here would be 32, okay? And for p times q squared, we would have, right, p times q squared would be, we can try a table here where we do a table of p and then all possible q and then the actual numbers. So 2 could go with 3, so that would make 18, 5, and I think that's it. So it goes up to 50 here. If p is 3, then q could be 2, and that's it. So that's 12. If p is 5, 5 times something, so q squared has to be less than or equal to 10. So q can be 2 or 3, and that gives us the numbers 20. And also 5 squared times 3, or 5 times 3 squared, which is 45. And for 7, we have 2 going to 28. At this point, 3 is too big, so we'll just go 11, 2, which gives us 44. And that will be the last one, okay? Perfect. So we have these numbers that we could reach. Of course, to get to 18, you need to start with a number with 9 factors. A number with 9 factors can be of the form p squared q squared or p to the 8, right? by the same logic, p to the 8 is way too big, so we need p squared q squared, and the smallest such value and only value is where p and q are 2 and 3 in some order, which gives us 36. Okay? So let me just draw a quick tree or like a graph just to represent what we have so far. So 12 goes to itself, and the numbers that go to 12 are 18, 50, 12, or we already have 12, 20, 45, 28, and 44, okay? And we can see that a lot of these numbers are really big. First of all, odd numbers can never be reached, so 45 is in its own park. And for the rest of these, we can notice that, are there any numbers less than or equal to 50 with 14 factors? Well, it would have to have like something to the 6 or something to the 13 or something similar. And of course, those will be too big. So 28 is on its own. 20, can a number have 10 factors? That would probably be of the form p to the 4 times q. And luckily, if we plug in 2, 3 here, we get 48. So 48 is the only example in 20 that in fact works. Let's take a look at 50. No number has 25 factors. So there we go. Or no number less than, or equal to 50. For 18, again, we talked about 9 factors. That's only 36. And for 44, of course, 22 factors is too much. So as we can see here, there are a total of, let's see how many circled numbers I have. Actually, I forgot one other number, which is the p to the 5th, right? 32. So let's count all of these. 1, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have a total of 10 numbers that go to 12, which gives us D.